Let's move to the next talk by Dara MacConville. I'm so sorry, I'm going to butcher any name I'm going to read. Oops, that was the wrong. Yes, apparently it's time to change the slide. That's what I got it called. So, my pleasure to introduce Dara MacConville. He's going to talk about modeling the total Python library in CSP.
Hello, yeah, as said, I'm Dara MacConville, and this is I'm a first year PhD student looking at software verification in general. And this is a short talk on a short paper I wrote along with these lovely people here, one of whom we have in the audience tonight. Hello, Matt. And it is modeling the Turtle Python library in CSP. Okay, so quick few definitions. Software verification. Making sure a program or a system does what you want it to, in general. And there's lots of different ways of doing this: formal languages, model checkers, theorem proofs, etc. We'll kind of look at. Oh, nice. We'll look at a formal language and a model checker in this. Robot, just the idea of an autonomous agent. A plan here, a set of instructions given to a robot to carry out tasks. And in our example, plans will look a little bit like this. Plans look a little bit like this. It's kind of a linear moment, the sequence of events. And we'll get to that in a second. Our goal to model a simple turtle, we'll get to that in a second, robot, its environment, give it a plan, and then verify that these plans are feasible in a sense by seeing if they match up with the environment before running, if they can indeed be run. All right, so turtle, I keep mentioning this. If you're not familiar, it's a Python graphics library. Well, it's lots of things, but we're looking at the Python graphics library, which you control a little turtle that draws it and moves around the screen, essentially. And it's based off like this older language logo and actual real turtle robots and things like that. But so this was an interesting choice, or a nice choice for kind of a simple robot system to model. It can do various movements, right? Forward, backward, it can change direction, left, right, and you can control the drawing. These are like the principal things it does. Pen up, pen down. If the pen is down, it's leaving a tray. It's leaving this diagram. You can see here a little turtle in action. If the pen is up, it's not drawing. And we're going to model that with communicating sequential processes, CSP. Now, if you're not familiar, it's a formal language for modeling concurrent systems. And it's made up, the key ideas of it are processes and events. Events are something that are communicated by kind of the environment, and processes react to them somehow. Quite a simple premise, but you can build up, anything good that's simple, you can build something more complicated out of it. Out of some basic operators go through, and things like combine with recursion, things like that. So the basic operators, there's plenty more than this, obviously, but the basic operators we're concerned with here are the most fundamental is the simple prefix, right? So you communicate or you receive or whatever some event A, and then you act like some process P. But it doesn't have to be a different process. You could be defining P like this, right? It could just be an infinite recursion like that, or it could be switching between another process, whatever. We don't want to just do things linearly though, right? It would be very concurrent. So we have the idea of external choice here. And you offer up as a definition, a choice between two processes, P and Q, and what choice is made will depend on the events that P reacts to or the events that Q reacts to. But we also want to run multiple things. So here we're going to use interleaving. So two processes, P and Q, will run in parallel with no synchronization. They're not going to communicate necessarily with each other. Just you start off two processes and let them run wild. If we define these processes, whatever, we might want to say things about them and reason about it. So perhaps the key thing to talk about is the trace of a process. That's the sequence of events that it communicates that happen to it throughout its lifetime, which doesn't have to be a finite lifetime. But so it's that plan we saw before. That's essentially a trace. And we say that a process P tracer finds another process Q if every trace of P is also one of Q. So these are the fundamental things about modeling language. What's our modeling approach? So what are the trade-offs you make or whatever. So you model a simplified turtle, as models often are, that captures but hopefully still the core elements of what this turtle agent. We bound the size of the world. We see there's some sort of finite limit on the world you're acting in. It's a grid world, like just the integer, or so the natural number plane. Unit movement to the points of this plane with orthogonal, right? Things you expect from an integer or a natural numbered world. The plan, the thing we give to the robot, are these traces we've talked about, effects. To simplify model design and make sure it doesn't get messed up, essentially. So we make the CSP events, the things that can occur in the CSP model, to mirror these turtle functions. And these abbreviations here, if you're familiar with the turtle library, you'll know that these are just the abbreviated function names of forward, backwards, left, right, pen up, pen down. The turtle library just allows these for brevity, and we use them here for the same reason. Well, why simplify? I mean, this is, any model is a simplification to some sense, and it hopefully makes implementation easier or indeed possible, while also capturing the core conceits of the system. And for instance, FDR, say, our model checker, it can test infinite states, has to explore the state space. So, what are you going to say about an infinite state space? But hopefully they're reasonable simplifications. And if you have a model, what does it look like? It's not just a single monolith. We have a main process that we make assertions on, we talk about, that kicks off the whole thing. But much like any program, it's made of multiple constituent processes, multiple constituent functions, if you want to think in a more programmatical way. And this modular design, it just, as it usually does, allows for greater flexibility, extensibility, swapping parts in and out, changing, developing. And it arose, just throughout the development process when I realized, the first things were a single monolith, and it was like, it's horrible to work with and extend. And it was, wait a second, there's better ways of doing this, and it makes reasoning about it easier as well. And so this main kind of kicks the whole thing off. It interleaves these sub-processes, and it kicks off the navigation and drawing as these two kind of separate concepts. They can run independently. They don't need to necessarily communicate with each other. And each of these kind of subparts handles their own respective events. So here you've got the navigator process, which it'll receive a forward event, left event, or whatever, and it'll keep track of the state, location, things like that, and it has kind of its own sub-processes that do that. And you can see here on the right, and we've got this turtle draw, pen down, whatever, and it'll receive the pen down process and say, okay, well, we need to move to this other step, which I think I might have labeled those wrong, but it'll receive the pen up process and it'll move to this other process. And this will allow for this back and forth, this mutual recursion, I suppose, between drawing. And this prevents, say, two pen down things coming in a row, because that's never a sensible thing to make. This model is integrated within a bigger tool chain to allow for ease of use, a bit more flexibility, and convenience, and then kind of extend what you can do with it. Creatively called CSP to turtle. So inputs, give it a plan and then a specification of the world. Currently, this allows for things like the dimension, some sort of goal, location, a few obstacles. Plan is submitted, it kicks off, it inserts the details into the model. The model is not, it doesn't know what world size you wanted beforehand, but now it knows. The model checker, CSP or FDR, is run on it, checks the validity of the plan in relation to the world you set up, and checks if the plan is executable, but also if the goal is reachable. It's kind of two separate things going on here, and it'll give you the results. So it'll say, okay, well, gave me an executable plan, but actually some sort of goal location is not reachable given the confines of this world. And if you have given it a nice executable plan, it'll also run the turtle, which is another nice reason for turtle. It has some instantaneous and visual obvious feedback. Some example usage, and with an impossible plan. So it doesn't look like this. This is just a visualization of the world. So we enter the world size in a nice 3x3 grid here, and the trace, which is the plan. So forward, it's asking you to go forward, then right, then forward. If you did that, you think you're facing this way first, and turn and you go right at it, right? Won't work. And you can think of this, by the way, as like the natural grid. So 0, 0. Extending up and to the right. So that's 2, 2 there. Yeah. Goal state. And some obstacles listed here. Impassable terrain, whatever, dangerous, whatever you want to refer to them as. And so we can see not a possible trace. You go right out, can't work in the confines of the world. But FDRs explore the whole state space and says, actually, well, it doesn't listen here, but I actually have found a trace that would get you a plan that would get you to the goal state. So even though your plan wasn't maybe good, it's still doable. It's not a lost cause. Here's an example where the plan does work. And so same world setup, but as we go forward, then we just, we mix it up a little bit, say, okay, put your pen up here, then put it back down. And you can see that the result of this is the actual turtle executed, just overlaid on the world. All right, great, it is working. And that was quick. But some future work, right? So the implementation is still quite limited. It's very much a proof of concept. But the good thing about that is that leaves lots of room for future work. So a time-based system, right? It's a robot. Maybe the world doesn't stay static. Maybe you have to get things done at a certain time. CSP does allow for this. There's a CSP top, I think it's called, that can do that. So that would be, or think maybe, the obstacles change in time or goal changes. So I think that would be a lot of fun. That'd be interesting to implement. And the plans themselves, right? We've seen several times already today, like what you want a robot to do, an agent to do is not necessarily linear. But CSP allows for non-linearity. So I think it would be, I'm not going to say easy, but it would be maybe a natural way of, you could specify plans with choice, non-deterministic choice, eventualities. That would be allow you to say a lot more about the possibilities of what the agent could do. And then, if you might be a lot of work to ask of the user and feasible to ask of the user to specify a whole, as we said, to specify a whole plan beforehand. But FDR can already do some findings plans. It checks the state space. So I think it would be a natural avenue to use FDR as a tool for sourcing a plan. And more like that, extend on that. That's just a link to the archive page. And that if you, give you the paper, and if you control F, you can just find the code in there, link to it, run it if you want. And thank you.
Thank you, Dara, for the presentation. We do have some time for questions. So is there any questions? Anna has a question. Oh, Anna?
Well, thank you very much, Fabio, for the presentation. Very nice to see other people using CSP and FDR. I had two questions, actually. Can you guys hear me all right?
Yes. Yeah.
Yeah, okay. So my first question is whether the work has advanced enough for you to actually deploy your plans in an actual robot and try it in reality.
That's a good question. I don't really have a robotics background, so
okay.
I don't know. I don't think it should be too hard, or perhaps it's a really naive statement. It's like, oh, the robot will work fine. Okay. I don't know. I'd be interesting though. Yeah.
It would be interesting, yes. And the reason why I'm asking is because I'm not very clear on how you have in your model, as far as I understood, an Olympian view of the world. Your model covers the environment.
Yes.
It's looking like it's abstracting a lot about the robotic platform and interacting with it via its API, which is fine. It is not a criticism, as well as the actual plan, which would be your view of the control software. But of course, when you want to deploy it in the robot, you only need to deploy the control software, the plan. So how do you see moving from this Olympian view of the world to the actual, getting to the actual code that needs to be deployed there, and what would be the consequence on your verification?
So how do I see it moving to like a real world environment where you don't necessarily have full information or full abstraction or whatever of the world? Or
not quite. Because your model has an Olympian view of the world, not all of it goes to the robot. So what goes to the robot? You don't deploy.
The robot has, so yeah, the robot has information of the world. It's in the robot's brain, so to speak. Like the robot knows that the obstacle, like, so it's almost like a, like where does the information reside? But yeah, I think it's fair to say that in this, the robot does have information about the world.
Okay, so it's particular architectural applications where there is a model of the world in the robot.
Yeah.
Okay, thank you.
Okay, any last question before we move to the next speaker? I do have one. So if I understood correctly, you passed as input to the CSP to title the plan.
Yeah.
And then it basically, and some information on the code, and then you will check whether this is feasible or not, and in case we generate code.
Yeah.
So in order to generate code, you need that the language that we have in CSP needs to match with the target language
Yeah.
of the parallel. How much of a discrepancy is there? So can you actually reach a point where you can cover the whole Turtle Python library with CSP?
And so there's definitely, so obviously that's the core functions, but there is other more advanced ones. You can do things like define a polygon starting at some point and things like that. Some of them are just kind of like there's like just ones that return information about the state of the turtle and stuff like that. It's not so interesting, but yeah, that's another thing I'd like to do in future work is some of the more advanced polygon recognition and say movement, like where you need kind of a memory of everything you've done, where the CSP at the current moment doesn't have that. So I'd say, yeah, the two kind of big missing things would be like polygon creation and then like kind of all the things that require a memory of the full trace you've done so far, where you have to like restore to a certain point or stuff like that. Those are the big discrepancies. But once, if those get covered, then that would be, I'd say, most of the actual functionality of the turtle.
Okay. Thank you. Let's thank the speaker again.